First you separate and then you integrate. Just follow these steps and you will do great. First you separate and then you integrate. Just follow these steps and you will do great.
Tis the season to be serving.
When I was solving equations, I was feeling amazing.
All right, today we're going to be looking at exponential growth differential equations. I want to begin this exploration with just a basic exponential growth problem, and kind of looking at it through the lens of how you would first saw these type of problems in pre-cal, and then we'll bring it into the calculus perspective. So you can see here I have an exponential growth function, kind of how you saw it expressed in pre-cal. And if you just look at the anatomy of that particular function, y of t equals 10 times 2 to the power of t, you understand t is the initial value. So if we're simulating a population, for example, 10 would be the initial population. And as you can see by the number 2, is that population is going to double for every consecutive value of t. And so you can see here illustrated in the table, at time t equals 0, the population is 10. And then at times t equals 1, it's 20. And then 2, it's 40, and so on. So there is a doubling for every time t. For the sake of argument, let's say t represents a number of days. So every day, this particular population doubles. And when you look at the function values of an exponential growth problem, when evaluated at the whole numbers, for example, those function values are reminiscent of a geometric sequence where there's a common ratio between consecutive values. And here you can see that common ratio is 2. And because of that, you may be inclined to say that the growth rate is 2, which is actually not the case. So we're going to kind of flip it and look at it from a calculus standpoint, and you'll see that the growth rate is actually ln2. So in a second, you'll get understanding why there's an ln involved in this, because really secretly inside of this 2, there's a e to some power in there, secretly inside of that 2, believe it or not, when we kind of look at this from the calculus lens. So let's take a look at how we express a differential equation from the calculus perspective. And the typical equation, the most simple fundamental equation, is that dy by dt equals ky. And what that expression is saying, if you remember proportionality as you learned in some of your elementary algebra classes, it's saying that the rate of change of the function is proportional to the function itself. So again, let's just start this off thinking about these things represent or simulate populations. The rate of change of the population is proportional to the population itself. So let's take a look at the differential equation we first looked at and equate it to the calculus lens, and it'll give us a better understanding of how we got that growth rate of ln2 that I spoke of. So let's take a look. All right, so here's the exponential growth function we spoke of earlier. And we mentioned, in calculus, we say a differential equation of exponential growth is of the following form, where the rate of change is proportional to the function of the population itself. And so we have mentioned without much proof or without much justification that for this particular scenario, that the actual growth rate, which we indicate with the letter K, we have indicated that the growth rate is actually ln2. Even though we saw the factors of the numbers to be 2, we said that the growth rate was actually ln2. So our claim right now is that the differential equation for this particular exponential growth function is dy by dt equals ln2. Okay, well, what does that mean in a very simple calculus way? Well, that means that if I take the derivative of y, I will get y times a factor of ln 2, right? Well, let's take the derivative of y. Okay, so we take the derivative of y, so y prime, well, 10 is just a coefficient, and the derivative of 2 to the power of t is ln 2 times 2 to the power of t. And if you see from the derivative, what we have is we have y, and again, y is 10 times 2 to the power of 2, and that y is being multiplied by ln 2. So that there demonstrates that indeed the proper value for k, which we call the growth rate, for this particular differential equation is indeed ln 2. So let's take a closer look into these exponential growth differential equations and get an understanding of why that ln 2 is there and why there's secretly e to some power near, as was alluded before. All right, so again, there's our base model for an exponential growth differential equation. And this is a separable differential equation. And so we can solve this particular differential equation by separation of variables. So let's go ahead and separate and solve it. So this will be dy over y equals k dt. And you know the saying, first you separate, then you integrate. So the integral of dy over y would be ln y, and the integral of k dt would be kt plus some constant. And therefore y would be e to the power of kt plus some constant, or e to the power of kt times e to the power of c. And of course, e to the power of c is just some constant. So that would be c times e to the power of kt. And so this is the general solution for exponential growth differential equations of this form. So call this 1 and call this 2. So 2 is the general solution for 1. So let's look at this a little bit closer. Let's look at the solution a little bit closer and name some things. So we're claiming that the general solution is c times e to the power of kt, where k, of course, is the growth rate, t is the time, e is a constant, and we want to get another better perspective of what c actually equals. So let's plug in 0 for t. So if I plug in 0 for t, and y is a function of t, of course. I didn't write y of t, but y is obviously a function of t. And so if I plug in 0 for t, this value will be y of 0, and I would have c times e to the power of 0, or e to the power of 0 is just 1, so I would just get c, meaning c is actually y of 0, which is the initial value. So c is actually the initial value of the problem. And so in many cases in population growth, that would be indicated by P naught, or other places you'll see it represented by A naught or something to that particular fact. So I'll represent it as A naught here. And so y is A naught times e to the power of kt, where A naught is the initial value or the initial population, k is the growth rate, and t, of course, is the time. Now, let's talk about the values of k in different particular situations. So a lot of time in these studies, we want to know how long it takes a particular thing to double. That's considered pretty important information in a lot of these exponential growth problems. And if you watched it, if you, of course, I'm pretty sure you have watched the news when the whole COVID-19 thing was unraveling. It was always a prominent thing on the news with the number of days it was taking the number of cases to double. So this doubling time is a pretty significant thing. So let's say, for the sake of for a hypothetical, let's say that our population doubles at time t equals 5. Okay, so I'm really not going to specify whether t is in seconds, minutes, hours, weeks, whatever, years. I'm just going to say t for right now. And let's say our population is doubling at time t equals 5. Okay, so what does that mean in terms of k? All right, so y is a naught e to the power of kt. And when I say the population doubles when t is 5, that means that the value of y is going to be 2 times a naught when t equals 5. So 2 times a naught equals a naught times e to the power of 5t. Excuse me, t, that's 5 is t to e to the power of 5k. Please forgive me, 5k. In fact, let me rewrite that. So 2a naught equals a naught times e to the power of 5k, because again, I'm plugging in 5 for t, because we're saying it doubles when t equals 5. And let's solve for k and see what happens. So these a naughts will cancel, and we'll get e to the power of 5k equals 2, which means 5k equals ln 2, which means k equals ln 2 divided by 5. So anytime you're in a doubling situation, k is going to be ln 2 divided by the time it takes to double. And if you want to talk about something tripling, then k would be ln 3 divided by the time it takes to triple. And so this is an easy formula for k, but let's also look at a formula for the doubling time. So let's say t sub d is the doubling time. And so we know that k is ln 2 divided by the doubling time. And so that means that the doubling time is ln 2 divided by k. So if we're in a doubling situation and we need to find k, k of course is ln 2 divided by the time it takes it to double. Or if we know k and we need to find how long it takes to double, then the doubling time is ln 2 divided by k. All right, let's look at a couple of problem situations and solve them. All right, so we'll start with this first example. This first example is a pretty simplistic example. And so it says dy by dt is 8y, and if y equals 12 when t equals 0, then y equals what? So when they tell me dy by dt is 8y, that means k equals 8. And again, our solution for y is a naught times e to the power of kt. So we know right now k is 8. And only two things we need to know to write our answer is the value of k and the value of a naught. And it tells us right there, if y equals 12 when t equals 0, that's telling you 12 is the initial value. So that's our a naught. And so our answer would be 12 times e to the power of 8t. And really, it's the only answer that makes sense of those particular answer choices. So let's look at another problem. Okay, so it tells us population y is growing according to the equation dy by dt equals ky, where k is a constant and t is measured in years. If the population triples every 3 years, then the value of K is. Okay. So we're solving for K, and the population triples in K years. So this was mentioned, it wasn't written, but this K is ln3 over, say, TT. So ln3 over the time it takes it to triple if we're talking about tripling. It was ln2 when it was doubling. It's ln3 when it triples. Well, in this case, it said it triples every 3 years. So K is ln3 over 3. And so that's a calculation you'll make in a calculator. So let's calculate in the calculator real quick. So we have ln3 divided by 3. So approximately 0.366. All right, so that was fairly easy. And so this will be the last example we'll look at. And let's see, bacteria has a population of 8.3 million at time t equals 0, and a population at 11.3 million at time t equals 5. If the bacteria's population is increasing according to the law of exponential growth, what would the population be at time t equals 9? Okay. So let's take a look at this. So the initial population is 8.3. So we can say y equals 8.3 e to the power of kt. And y of 5 equals 11.3. And they want me to find y of 9. All right, so this is the situation that I have now. You know, to find y of 9, I need to plug in y into this function. This function, the only thing I don't know right now is the value of k. I know a naught, I just don't know k. So I need to figure out k. So I'll use this information to solve for k. So I'm going to plug in 11.3 for y and 5 for t, and then solve for k. So this will be 11.3 equals 8.3 e to the power of kt. Excuse me, e to the power of 5t. 5k, excuse me. Making that mistake a lot today. E to the power of 5k, which means e to the power of 5k is 11.3 over 8.3, which means 5k is ln 11.3 over 8.3, which means k, of course, is this value divided by 5, ln 11.3 over 8.3, 8.3. I'm having some issues here. Divided by 5. Let's calculate that in our little calculator. So ln 11.3 divided by 8.3, and that's divided by 5. So let's say 0.062. In fact, let's just store this. Let's store this whole thing to k. Where's k? So we'll just store that to the variable k. So we'll just say that's k for right now. So again, we want to find ln 5. So on here, I'll write is about 0.062, 0.062. And so that means our equation is y equals 8.3 e to the power of 0.062 t. And the thing they want me to find is y of 9. So y of 9 is 8.3 times e to the power of 0.062 times 9. And so to type that in the calculator and with the actual value of k unrounded, so this will be 8.3 e to the power of k times 9. So approximately 14.464. All right, so that will conclude this particular lesson on exponential growth differential equations. We'll see you next time.
Specialized in science and math, original black men, busting thoughts that pierce your mental, the fierce, ripping your section. Vocal toe to toe, impeccable, splitting your back, son. Simple as addition and subtraction, black thought, the infinite relax one.